welcome to the 6 practicals of Introduction to Structured Programming. Today it's us again, so Julia and Michael. What is the plan for today?
Well, again, as always, we have some organizational matters for the practicals. Then Michi will present to you some recap from last week with FGS and GetJar. I think you didn't manage to get to the example last week.
Yeah, so we present the example that we planned for last week.
Yeah. Then we'll look again at the 2D arrays, especially now that we know what pointers are. I think that 2D arrays then are a bit more interesting than before. And also we have some special cases with call by value versus call by reference with structs. And then at the end, if we get to it, maybe not, we'll talk about string copy because we didn't mention this yet in the practicals.
Okay, so the organizational matters, what is important at the moment?
Yes, so please keep in mind that next week on Wednesday, this is the deadline for assignment 2. As always, at 18 o'clock. I can't recommend enough that you always push to GitLab your latest version of your assignment, because it could get lost in some way, like your laptop, you lose your laptop or something like this. And also next week on Monday, we can have a question hour, but at a different time from 10:15 to 12:30 in the Hörsaal I7. And yeah, it will be very similar to last time. We'll repeat important concepts at the beginning, then you will be able to ask questions in general and also about your specific assignment. Then coding session 2 and homework 2. Now this is important because you only have 3 days to register for a coding session.
So this is Sunday at 6 p.m.?
Yeah, so at Sunday you need to be registered for a coding session. So maybe already do it today in between the practicals and the lecture. Search for a suitable time slot. And also homework 2 should also be available today. But again, you don't have to hurry with the homework that much because you have time until your actual coding session slot begins. And the topics this time will be computational thinking and algorithms.
Okay, then let's get started with the coding part. And last time we discussed FGS and GetJar in a bit more detail. You also need at least one of those 2 functions for assignment 2. So let's start with a quick recap. So we had those 2 functions, FGS, where we had 3 parameters. The last parameter, this interesting file star, this was to specify from where we want to read, and we said this will always be stdin because we want to read something from the terminal. And then we had this char pointer where we would like to store the input. So this is then the buffer where we want to store it, and then the size here. So how much of the input we can store into the buffer specified here. So FGS always reads a string, so multiple characters at once. And GetJar, as you should already know, also from previous practicals, reads exactly 1 character from the input, and the return value here is this integer. Why is it an integer? We also talked about end of file, and we said, okay, in the case of end of file, so this is Control D. If I type Control D in the terminal, then this would be an end of file. There will not be any further input from the user. In this case, GetJar returns -1 as an integer and not as a character. And we also said that FGS indicates this end of file and it will return null in this case.
Yeah, that's a common cause of an error. If you assign the return value of GetJar to a character, then you won't be able to distinguish the end of file anymore. And then you might introduce some errors in the end of file case for your program.
Okay, then let's have a look on this in an example. So we do a bit more coding today than last time. So the goal basically is the following. I read an input, and let's say I read ISP as the input, and then I read two characters. So a character to replace. So we read in an E, and another character where we want to replace this character with. So in this case, for instance, an I, and then the output should be ISP. Like we update the version of our course. So we have two inputs, and then we basically check the input string. Does the character E appear somewhere in the string? And if yes, we replace it by the I. And yeah, we check this for the whole string and then write the output here. Okay, this is the whole program. And yeah, I think most of the things should be already familiar. So let's start. I want to read an input. Okay, so I will write the function, like I want to read a string. So I write the function read string for this. Okay, let's keep it like this for the moment. Okay, read string. I want to implement this now. Okay, if I want to read the string, I want to use fgetS. Okay, so write fgetS. Okay. Okay, the first parameter is difficult. Maybe start with the last one. We want to read from std_in, so from the terminal. But we want to store the input somewhere. So we need an array. Okay, let's make a buffer. So character buffer, an array of, let's use constants of buffer size and define the constant immediately. So usually you would use now, I don't know, 20 for the start or something a bit larger. I will use simply 5 here because I have afterwards visualizations that I can draw this without need to draw like 20 characters somewhere. Okay, so we have the buffer here, fgetS. We want to read in the buffer. Okay, how many characters? We said buffer size. Okay, now we read it, we store it in the buffer. I would like to get the buffer into the main function. So what could I do that I get the content of the string into the main function? Any ideas? Yeah. Okay, you say we could use a return value. Can I return an array from a function? Okay, yeah. But you said the right thing. Probably we should not have the array here, but we should put it in the main function. Okay, so let's put it in the main function.
Yeah.
Sure.
If you don't know why, I think last time you did really nice visualizations about what happens if you try to return an array from a function.
No, we actually didn't do this, but we said how to pass it to a function. The return.
Okay, the passing to a function.
Yeah,
yes.
but yes, this is the right thing. We need to put it into the main, and now we need to pass the array by reference because we would like to write into the same array in the read string function. So I would pass the array buffer here, and I would get here. We said last time we could either write it as in array description or even as a pointer. Would this now work? Do we really write into the array here of the main functions? Do we have call by reference, or do we have now call by value, and this is just a copy of the array of the main function? Somebody opinion about this? Yeah? Yeah, exactly.
Yeah, I think it's nicer to see if you write it like a char pointer like you did here, but even if you use the square brackets to indicate an array, it's still a pointer, so it's just the same as a pointer. It's always just a call by reference, not a call by value.
Yeah, thank you for working with us. Okay, so it should work. Let's maybe %s. Printed already the buffer, and maybe let's compile it first. Compile the program, and I write now directly ISP, and it prints also ISP, so this is working. Now we said about this end of file thing, how can we handle this now? Because if I would execute my program and press Control D, okay, it terminates now, but maybe I would like to specify an error message, end of file reached or something like this. How can I get this? And we said, okay, in this case, fgetS returns null. So we need the return value of fgetS, and the return value of fgetS, if I just hover here, this is a character pointer, as you can see, on the very left here. So char pointer return value of fgetS, and then how can we get this value now into the main function? Now we can return it. We can specify return value here, also return the character pointer from read string, get the return value, and if return value is null, then we could, for instance, write EOF reached and terminate maybe the program with a specific error code here.
So we just said that the character pointer, we cannot return an array from a function. Why is this possible now?
Because we're now turning just a pointer, which is an address where the pointer is pointing to. An address is just a single value. We can return a single value and we can check the single value. But if we would like to return an array, we would like to return multiple values at the same time from the function, which doesn't work in C. Maybe I just want to...
And maybe also importantly, fgetS, if it is not an error, it returns just the same pointer again you pass to it. And the pointer points to the main buffer. So even if the function is then deleted the stack, it's no problem because the array lives on the main. Mm-hmm.
But we will just use it really for the null check. Just to make it a bit now more appropriate the program, I will just write here an additional printf. Okay, so this is the read string part. Okay, then I said at next I want to read the character to replace. So I write now a function, read, directly do the cool stuff, read char, and I start again like this. Let's see what we will need. So read char. Okay. What do we want to do? If we want to read just a single character, we will use now get char. And in order to be able to check for end of file, we will store it not into a character, but we will first store the return value of get char into an integer. So I use now maybe the name int char. Okay. Yeah. Okay, so we have this int char, and we can basically, we could return it like immediately at this case. So it's not really doing anything, the function at the moment. We just read a character and return it. But it makes sense. I will show you in a second. So we'll return it, and we'll write it also here. Int character is equals read char. Okay, and now I basically want to do this 2 times because I probably should name it the to replace and the integer replace with, because we want to read 2 characters. Okay, we'll store this as both as integers. We read the characters. Now I would like to also include here like a printf. I would like to say, for instance, I would have a enter char to be replaced in the first case. And in the second case, I would like to have another message here. So I could now write a second function where I do exactly the same thing and change the message here, but I could do also something different. I could just take the message and pass it as a parameter to this function. what is this now? This is a string, and we learned in the last lecture that this is a character pointer, so we'll call this a prompt, maybe, input prompt. And in the first case, this, we'll send this to the function, and in the second case, to take others place. Okay, so now we have really used the function for two things, yeah? And how can we print the prompt? It's a string, so %s and the prompt. Okay, and maybe just also print this here, %c to replace, %c replace with, that we have an output for everything. Okay, so let's see what we have. We read the character, we print the corresponding message, we return it as an integer, return it here. So why do we return it as an integer? We want to also check for end of file. So we check to replace if this is -1, and then we can basically do the same stuff again. And I can also do the same thing now for the second input. I will do this for replace with. Okay, let's try whether this works out now. I compile it, okay, it works. I run it. I don't know, I'll just move a bit over because this is not always visible on YouTube. Okay, we enter a string. I enter now ISP, as said before. Enter char to be replaced. I enter the E. I couldn't enter a second character at this moment. Has somebody an idea why this was the case? We talked about this 3 weeks ago, 4 weeks ago. Yeah? Yeah, so there is still the new line character and the input buffer. We can get rid of it if we just write while get char is not the \n. Then we repeatedly read from the input buffer, and once this condition is not fulfilled, we have reached the \n, so the input buffer is clear and we can again enter something. Let's try it again. So ISP, enter the E, I enter the I, and then I get the right results. And now check for the end of file thing. If I type Control D at this moment, we print E of F reached and terminate the program. If we enter some string and then press Control D, if it would work, let me do it again. It's not working. What have we done wrong? Okay, yeah, I see it. I see it. That's not too obvious now.
Who sees the problem?
Yeah.
No, we have integer here and integer as the return type.
Oh, this is okay. Yeah.
It's a bit hard to see.
This is not obvious. Yeah. Okay. I was also not aware at this moment. If I press Control D here, then in int char I get -1 because we have read EOF, end of file. But then I do this loop here and repeatedly read from the input buffer until I reach the \n. But I said before, there is no more input. Like I've read end of file, there will not be any further input. So getchar would always return -1. So this loop will never reach \n, so it will never terminate. So I produce now an endless loop in my program, which is bad. So let's say if the input character is unequal to, I could also use the constant here, EOF. In this case, I clear the input buffer. And if I have already reached EOF, I don't need to clear the input buffer because there is no input buffer anymore, basically. Okay, that's why we test our programs. Okay, run it again. Okay, ISP, this worked. Now I type Control D. Okay, now it terminates and it prints EOF reached. So really, we got -1 here. We skipped the clearing of the input buffer. Go to this condition here. See, it's -1, or if you like EOF, this is equivalent. Print EOF reached and terminate the program. Okay, I was able to fix it. Maybe just replace it also here. Okay, now we're almost done. So we have our two inputs now, and now I would like to produce the output ISP. So I would like to iterate over the input string, and I would like to replace every occurrence of this character with this character. So also this, we'll also do this in the function, or maybe, let's leave it here, maybe it doesn't matter. So how have I called the function? Substitute characters. So what does this function need for an information to replace everything? We need to pass the buffer, because, I mean, we need to know the string where we want to replace something. Then we would like to pass the to replace. Yeah, so we would like to search for this character, and then we also pass the replace with. Okay. Let me copy this. Okay, I think I don't need a return value. The first thing is the character pointer buffer. I have always, let's call it string, I think. Doesn't matter. Then I have the character to be replaced. This is a character, and char replace with. So, recall, last lecture. This is an array. This is passed by reference. If I change something in here, then I will change the array of the main function. This is a character, also this is a character. They are passed by value. Those will be copied. If I would change something here of those two variables within this function, this change would not appear in the variables in the main function.
Yeah. And it's really good if you understand that, but it's really great if you also understand that the character pointer string here, the pointer, so the address is passed by value. So we copy the address, but the address still points to the same string. So we say by reference to the string.
Mm-hmm. And now how can we do this? This is also like a basic algorithm now. How can we substitute the characters? We should iterate over the string. So I will make now a for loop. Okay, we start with position 0. We check, do we need to change something in the string? If not, continue with position 1, position 2, position 3, and so on. When can we terminate? Let's leave this open for a second. So I need to, let's try to do here. We need to do this. When do we terminate the loop? This is still open. And now, maybe do this in a separate function as well. So call this check and swap character. So we would like to pass now the string at the position, where we want to do the change, or check if we want to change the character. So we would pass like the E, then we will pass the S, then we will pass the P, and so on. And then, we again need to know, is it the character that we want to replace? And then we would like to replace it with the character immediately. Okay. Maybe fix this first. So I go over the input now that I have read, character by character. When do I know that I can stop? Yeah? Yeah, when we get the null terminating character. So we check, is the string at the position equal to 0? Or you could also write it like this, as a character, the null character. At this moment, we want to repeat it as long as this is not the case. If we have reached the null character, we would like to terminate. As long as we haven't reached it, we would like to continue here. Please this is important. In this case, we would like to iterate over the characters in the string and not over the characters in their underlying array. So if this buffer size would be 5,000 and our input would be 10 characters, then we still only want to look at the first 10 characters and not in the whole 5,000 character long buffer, because we don't even know what is written there. Maybe it's not even initialized. So if we work with strings, we really need to check for the null terminator in this case and not refer to the size of the buffer where the string is located. Okay, so that is why we have this condition. Okay, now last function, I promise. Check and swap. Swap character. So I have the character, how have I called this character? Candidate character. Then the char to replace and the char replace with. And now I would like to check, is the candidate character the to replace? If this is the case, then we write candidate character is replaced with. Okay, so we have now a function that replaces the values of the string if this condition is satisfied. Any remarks? Does this work?
Mm-hmm. Yes.
Yeah, we need a pointer for the candidate char. Why is this the case? If we would just pass string at I, we would again pass the character. This is a character. It would be copied, called by value. We would check if the copy is to replace, and then we would replace the copy with replace with. But this change is only in this variable and is not related to the string. So for this reason, we need to pass this character by reference. So instead of taking string at I, we need to take the address of this, receive a pointer to this address, such that we can modify the value behind this address. And in this case, of course, we need to dereference the address that we can access the value behind it. And also here, we need to dereference it that we can write into the value behind it. I have a visualization, so we maybe check the program first. If this is now doing the correct thing. If I type ISP, and I want to replace the E with an I. I have not printed anything at the end. This would be a good thing. Maybe print the string again. The buffer again. Whole thing again. ESP, E, I, and now, okay, we see we have the 4 printfs, and in the last printf we indeed have ISP instead of ESP. So this worked out. Yeah, we got it replaced. And now maybe if we want to look at these 2 functions in particular, I also have a visualization for this. So we have the main function. So I think I called it now buffer. I'm sorry. This is just an array where the input is living in. Then I have the character to replace. There is the input E. And the to take place, there is the input I.
This was the replace with in your code now. The to take place.
Yeah, okay. Okay, yeah. So this is that we want to replace, and this is which gets the place. And then we have called this substitute function. So the substitute character function, which has these 3 parameters. So the first parameter was the string, and the string is a character pointer. And this pointer points to the buffer here.
Yeah, to the beginning of the buffer.
To the first character of the buffer. And additionally, we have the 2 characters that we passed. And this is not a pointer or something. This is now really a completely unrelated variable to this. These are 2 separate positions in the memory, 2 different E's. and the same for the I, and then we also have the iteration variable here for the for loop. And then we call this check and swap character thing. And the check and swap character thing, what do we pass? The first thing is this candidate character. This is again a pointer. Where does it point to in the 0th iteration or first iteration? The iteration where the I is 0. It points to the first character in the array. And the two characters are still just passed by value. Again, copies of these, and these are copies of these. So they live now 3 times in the program, actually. And now, with this statement, we basically check if the arrow where the arrow points to is the same as the value of to replace, and then we do the replacement. So in this case, we go here. We see this is an E. This is an E, they are the same, so we take the I and also write it at this position. Oh, this is changed here. Everything else is the same. And then in the next iteration of the for loop, so if here the I equals 1, then this is, oh, I should have changed it to 1 actually. Yeah, here is a 1. Yeah. But the important thing is we now passed the address of the next character in the array. So this points now to the S instead of the I. And now we do again the check, oh, S is not E, so no replacement. We increment the I to 2, so this would be a 2 now. And now the address here points to the third or index 2 character in the array, and so on and so forth. Yeah, okay, this is the last visualization. Continue with 3, and then 4, we don't pass it anymore because we've reached the null terminator. So we always have this character pointer pointing into the array where we want to modify something.
Okay, so maybe with this visualization, this having a pointer to each element in the array, last time in the lecture you heard something about pointer arithmetic. And yes, this is very related, because we somehow saw that adding something to a pointer is like indexing into an array. So in the last lecture, maybe you had this array here. Now this is a character array with 1, 2, 3, 4, 5. You could also see this as a string, but let's interpret this as an array now. And then I have this, all I do is just take the pointer to the array, because our array is just a pointer, and add 2 to it. That's what you saw last time in the lecture. But now the question is, how does this look in the memory? Because I think you heard last time that adding 2 to the array pointer is the same as like indexing into this array with the 2. So how does this look in the memory? Well, I've written down some addresses here now. The real addresses in your program will look wildly different. This is just for illustration. But let's imagine the array starts at address 100 and then goes up to 101, 102, 103, 104. And in each cell, we have the correct character. Now, what do we do? Well, okay, let's think about it. So the array here behaves like a pointer, we said. And now if we add 2 to it, well, it points to 100. We add, so the address stored in this not really existing pointer is 100. We add 2 to it. Now we would expect to get a pointer which stores the address 102. And this is what happens here. We have this pointer, and we stored 102 in this pointer. And as we can see, this is the address of the element with index 2. So adding 2 to the pointer really does the same thing as indexing at index 2. And you could also imagine like the pointer points here to the 0. We add 1, it points to the 1. We add 1, it points to the 2. Okay, but now we looked at this with the addresses. Everything seems fine. But you might have already noticed that here the pointer is at address 92. That's because the pointer is 8 bytes. And each address indexes 1 byte. So what happens now if we make an int array? Now every element in this array is 4 bytes. And we add 2 to this pointer. What we might think now is like, okay, we have this array. Let's say it starts at address 84. Then this one here is 4 bytes. The 2 is at 88. Then the 3 is at 92. And I drew this 5 here up here really big, so you can actually see the integer takes up 4 bytes of memory. But what happens now if we take this array pointer and add 2 to it? Well, the address of the first element is 84. So if we add 2 to it, is it then like 86? But 86 wouldn't even be a real integer because it's somehow here in between those two elements. So the address is not really aligning with the correct addresses of the array. So does adding 1 to an pointer to an array only work if it's a character array? It turns out it works for every array, because what really happens is that when you add 2 to a pointer, it automatically multiplies the size of the underlying type of the pointer, or the type of the elements we have in the pointer. So because the integer is 4 bytes, if we say this address 84 plus 2, we don't add 2 to the address, but we add 8 to the address. Because we multiply 2 with the size of the integer, which is 4, so we get 92. And 92 is then the correct address for the second element. So again, adding 2 to this array pointer is the same as indexing the array to get the second element. And this happens automatically. You don't really need to think about this, that this happens. So yes, this here just does what you expect, and adding 2 to the pointer is just the same as indexing at the second element.
So you basically proved 0 plus 2 is 8.
But yeah, so it's good to be aware of that the pointer arithmetic for different types does different things to the underlying addresses. But if you always think about pointers as arrays, when you add something to a pointer, it's just as incrementing at the size of the element steps, so you always get the next element in this array.
So we would like to see now how we can use this in practice. So switch back to my example. There is like one position where we can use this here, and basically in the substitute character function, we said, okay, we take the string at position I. So this is then the concrete, the value, and then we take the address of the value. And now this is like a bit awkward because we're doing like going to with the string pointer, going there, we are already at the element, and then take the address of this. And with the pointer arithmetic, we can just simply write, I take my string pointer, and instead of pointing to the 0th position of the string, I add I. So I increase this pointer, the address basically there, by as many characters as I want to go further in the array. So I could simply write string plus I. So these two expressions, I just write it again, this end string I is the same as string plus I. Now you can decide what looks nicer to you, but this is completely equivalent as we have seen before. But this is not a large change. We can write even the whole loop using pointer arithmetic. And we can do this as follows. Instead of having this I here, where we always go to the 0s, to the first, to the second, to the third element, we directly work with a pointer that always points to the correct element. Maybe I just start with the visualization in this case. So basically, I would like to have a pointer here, I called it now iterator, that points at the beginning to the same address as the string is pointing to, namely to the start of the array. Okay, and then I increment, so like in the next iteration of the loop, I would like that the iterator, this pointer, is pointing to the first element, or like the element with index 1 in the array. And in the next iteration, I would like that it points here. So I don't have like this I that says I'm at position 0, 1, 2. I directly want to have a pointer that points to the element that I want to consider. So how can I do this? I can use a for loop, but I use now a pointer here. So I take a character pointer, again character pointer, we want to point to characters. I call this now iterator as in the visualization. And in the first iteration, if you look again at the visualization, it should point to the same element as string does, and string is our parameter of the function, so we can just assign it to string. So both are pointing to the start of the array. Okay, let's leave the condition again out. What do I want to do within each iteration? I would like to take the iterator and add 1 to it. Okay, and I just can also abbreviate this by using iterator ++. Okay, then I can call the check and swap function. And now I don't need to pass the string plus like how many characters I have visited so far, but instead I directly pass the iterator, because it already points to the character that I want to consider. And this is then an address. This address gets copied here. And with this address, I can now refer to the correct value that I want to check. So I have this iterator here. And then, okay, the rest is the same as before. Replace with. What is the condition now? The condition is the character at the position where the iterator is pointing to the null character? So I take the iterator, this points to the current character, I dereference it, I look at the value that is at this address, and if this value is not the null character, I repeat. If it's the null character, I want to terminate the loop. Okay, and now this is exactly equivalent as before. I just try it, E and I. So we again get ISP. This is working. And again, to make this, we have to look at the visualization. We really have this iterator that points to the element. I increase it by 1. So as you said before, this will go to the next element in the array, so it will point to the S. I increase it by 1, it will point to the P. And I increase it by 1, it will point to the \n. And then I increase it one more time. I basically get the null, the terminating null character. In this case, I don't call the check swap function anymore. And I have looped through my array without using an index.
Yeah. And as we've seen, now with the pointer arithmetic, this also works for any type of array. So not just for characters where it happens so that the address is actually just increased by 1. This also actually works for integers, for doubles, for anything. Because always when we add 1, we actually increment by the size of the element to go to the next element.
Mm-hmm. So basically for a 2D array, yeah?
Yeah, we'll look at this now.
We look at this, yeah, this is the next topic. But maybe before we start, any further questions? I mean, this was not so easy. Maybe it's also a good chance that we can take a breath. Yeah, this was a lot of things that we discussed at this moment. Okay, it looks okay. Then start with your 2D arrays, please.
So maybe just so that we have some context, recall the temperature example from last time. We collected temperature data in a 2D array, and what we did was, we had 3 measurements per day, and we wanted to store multiple days in an array. So each day was an array, and also we had an array of all the days. So we used a 2D array.
You can remove everything now if you like. My nice code is gone.
Okay, so how does this work? I'll call this now my array and not temperature, because in the visualization it's also my array.
No, you don't make the same mistake as me. Okay.
Yes. And now, so what did we have? So this is now the array of days. And we have 2 days. And on the first day, now I'll use the same values as in the visualization. We had these 3 measurements, the temperature in the morning, and in the afternoon and in the evening. And then here I have those. So this was a 2D array from last time, or something like this. I think we did it with integers, but it was very similar to this. And we said in the memory, it actually looks something like this. And we even did this little trickery where we, with the indices, we just continued counting from 2 with 3, 4, 5, and never changed the first index here, and it still worked. So we actually saw that it is laid out in the memory like this. But now we know that arrays are also pointers. So it does not really look like this in the memory. Or it does look like this in the memory, but if you think about it like this, what happens if we pass my array to a function? Or if we assign it to a pointer? Then now this image we have in our mind doesn't work anymore, because you always said these are fake pointers, the arrays. So it actually looks something like this. As you can imagine now that we have a 2D array, we have 2 dimensions here. And what happens is that now this is a double pointer, so a pointer to a pointer, because the my array, if we dereference this, we still get a pointer which points to the same element, and then we need to dereference this again to actually get to the element. And again, as for one-dimensional arrays, these pointers are nowhere in memory. They don't exist in memory, but they still behave like one. So they are consistent with if we work with arrays in functions, because then they are actually pointers that are in memory. Maybe I'll write this down. So now I would be interested in, let's check this visualization so I do the right thing. What happens if I write my array plus 1? Because we said pointer arithmetic, but what actually happens here when I do it like this? Because, okay, we have doubles in here, but also it's a 2D array. So when I increment this pointer here, right now we have a pointer which points to this pointer which points to the first element. But if we add 1 to this outer pointer here, does it point to the first character, to the first element? Well, we'll see. The second thing I want to look at, what happens if we dereference my array and then add 1 to it? So, and then maybe just for completeness, what happens if I dereference my array 2 times?
Well, the last thing is probably the easiest thing.
Yes, we said my array is a double pointer, so dereferencing it once, we get my array 0, so with the first dimension indexed at 0, and dereferencing it again, we get this here. So I'll write it now write it down like this. This is the same thing as my array indexed at 0 2 times. So we get the first element. Now, what happens in these two cases? Well,
many calculations, yeah.
It's a bit more complicated now, but let's think about it. We have my array plus 1. So let's start with this here. Well, we know that this 1 actually somehow includes the size of the array that this pointer points to. But what is the size of the array this pointer points to? It's not double, because we are not doing size of my array dereference 2 times, so just size of this 4.2, but we are doing size of dereferencing this my array once. So we're doing size of this here. What is the size of my array 0? And well, my array 0 is this whole array here. So what is the size of that? Well, it's 3 times the size of a double, because we know the size of the array. It's 3. It's 3 times the size of the double. So we actually go to the correct position if we do my array plus 1, and we go to my array 1. Because we add the size of this whole array here, this pointer now jumps up to here, to pointing to this pointer which points here. So, as we might expect, this is the same as my array indexed at 1, which gives us a pointer to this whole array.
Maybe you should write one pointer star on an address that it's really the same thing.
Oh yeah, like this.
So the address of my array 1.
So, no, wait, it's really this. Yeah, okay, it's the same thing if we do it like this, yeah. Okay, then what happens if we do it now like this? If we first dereference and then add 1, well, now we are just in the case of a one-dimensional array. Because when we dereference my array once, this is the same as indexing my array at 0, which just gives us the first array. And then if we add 1 to a pointer to an array, we get the second element. So on this now really is the size of the double. So this is the same like the address of my, of my array 0 indexed at 1. So of the address of this element. And well, now this might look a bit more complicated, but if we dereference this once, you can imagine like this dimension vanishes and we just have an array of 3 elements. And then it's like in the one-dimensional case, we add 1, we get the second element, which is 12.7. Okay.
It seems a bit complicated, I must admit. And I think it is also, if you think about it, if you really want to understand what is happening behind the thing. Because on the one hand, this 2-dimensional array is like this consecutive block of memory where we do not really have like these dimensions. It's just everything is behind in the memory. But on the other hand, we would like to access it like a real 2-dimensional array where we first go like to the first dimension and then go to the second dimension. So it's like this double pointer structure here. In a few weeks, we will also see a second type of 2-dimensional array, which then is not necessarily contiguous in the memory, but it will have the same ideas with the pointer indexing.
Yeah. I mean, also if you think about storing pointers to strings in an array, then you can also really have the actual addresses in the array, and it's not just all fake pointers. Maybe we want to access the element at 11.2. Well, we can do this like we did before. We, in the first dimension, we want the second array because this 11.2 is in the second array, so we'll get write 1 here, and then this 11.5 is at the
do it. We don't. I don't think we have a visualization.
We have a visualization.
Oh, okay, then do it for the.
Okay, we want to access
6.7.
the 6.7. Yeah, so we want to access my array at this element, so we get into the first array, and then 2 for the last array, because 0, 1, 2, we are here. Okay, this should be clear, but now I want to do the same thing, but with pointer arithmetic. We've already seen that this works for normal arrays, that we can just add I and then dereference this whole thing to get to an element instead of using the index syntax here. Well, how does this work? Maybe now let's also look at the visualization first. What do we want to do? This my array here, we do not want this outer pointer to point here, but we want it to point to the upper array. So to the outer pointer we'll add 1. This will add the size of the whole first array. We'll get here to the my array 1, and then to this, so we get this pointer here if we then dereference this. And then we have another pointer to which we add 2 to get to the 6.7 here. And this now is again like in the one-dimensional case. So what do we need to do? If we add to the my array, if we add 1 here, we get a pointer to the second array. And if we then dereference it, we get a pointer to the second array. So now this is a pointer to the second array because this is a double pointer. It's a pointer to a pointer. We need to dereference it once, and we still have a pointer to this array. And then we add 2 for the second dimension here. And then dereference this whole thing again. And now if we are lucky, it should actually print the same thing. Yes.
Mm-hmm.
So, yeah, and actually you can see that now the order in which you write the indices, first the 1, then the 2, is exactly the same in the pointer arithmetic. We first add the 1 to skip the first outer array, and then the 2 to skip the 2 elements in the second array. Yes, now just one more thing about 2D array. If we now have any function, how would we pass a 2-dimensional array? Well, okay, we could try something like this. And now in here, just dereference something like, do the same thing again. Okay, now we already have an error. But does anyone see the problem why it can't work like this, that we pass an array to a function like that?
Mm-hmm.
Yes, the size of the array. So now we need the size of the array in the 2-dimensional case now, because for the 1-dimensional case, it wasn't important how big the array is to pass it to a function. If we just have a 1D array, we can just write the square brackets like this and it works. But for a 2D array, we actually need the size of the inner dimension. Because if we go back to how actually we access an array, this is a very similar thing to what the compiler needs to do. We need the size of the dereferenced array once, so the size of the whole first array.
because we basically want to replace the size of the pointer with size of the data type, which is behind, times how many elements are stored in this dimension.
Yeah.
So
we need the 3. Because, and for the one-dimensional case, it didn't. Yes. Mm-hmm. Yes. Mm-hmm. Yeah. So isn't the pointer always 8 bytes? Normally, yes, a pointer is of size 8, but the my array dereferenced ones is not just a pointer, but it is a whole array. And if we have an array, then size of sometimes returns us the actual length of the array.
So
and that's why we need the size here, because in this function we also need size of to return the actual size of the inner dimension.
Also, I also say something here. So like my array dereferenced, yes, this is a pointer of some data type. Yeah? And the data type is now array with 3 characters. And so array with 3 characters means I need to increment by, with three tuples. So this means doing pointer arithmetic there, I need to add always 24.
Yeah. These are the very subtle things you need to know about C, because most of the times an array is just a pointer, except for when you use it with a size of, and you immediately created the array in the same function, then you really get the size of the array with how many elements are in there.
Mm-hmm.
And we actually need this here, because else if we want to index up here, we don't know how much memory to skip for the first array we stored in a 2-dimensional array. Therefore, we always need to specify this dimension here. And I think I also have some, yes? If you have like a 3-dimensional array, yeah, then if you want to index the outermost, so if you have something like this here, if you want to index the outermost dimension, you need to know the size of this dimension and then how many arrays are stored in the inner dimension. So you actually need to specify 2 dimensions, because you need to skip really the amount of arrays you have in the memory. Yeah, you have to specify all dimensions except the outer dimension, because you don't need this to actually calculate the address of an element in memory. But you don't need to know this for our course. 2 dimensions are enough. Yeah, and here I have this visualization. No, yeah, here I have this visualization once more, where we have the address of the first array. So
when you pass it to the function.
Yeah, so this was my array, and what we passed to the function is the address of this inner pointer here. And if we dereference it again, we are actually at the elements.
10 more minutes. Should we do the structs or the string copy part?
I think the structs are more important, but I'm not sure.
Then let's do the structs, I think.
Yeah.
Yeah, okay. But actually, this is also your example. So
I mean, you can do it too if you want.
No, you can do it better. Okay, so call by value, call by reference with structs. Maybe start with an array again.
Yeah.
So before we start with the structs, we take an array.
Again with the temperature example. So let's say, because I don't want to do this with a 2-dimensional array now, because I want you to understand arrays together with structs, and I think 2-dimensional arrays would be too complicated now.
Let me introduce the example while you're coding. So we just take now one day basically where we have 3 temperature measurements, and in the first part we have it now just directly in the array, and now we have the value 0 at the end. We would like to enter also the temperature in the evening. So we want to write this function log evening where we basically set the measurement in the evening. Okay, yeah. And let's write this function at next.
Yeah. And I think we already know how to write this.
Okay, so we pass the array. So we need a double pointer or double array as you like, both is possible. And you also have this measurement here. So we also need to pass the double. And then we simply go to the evening. This is the last value in the array with index 2 and set the measurement.
Yeah. And let's just recall this. This is the same as doing this.
Yeah, okay, so this is the same. Okay, but this is now clear what is happening basically.
Yeah, because arrays are always passed as reference. I think we've said this oftentimes. Enough now. So yeah, it seems to work. We get 4.5, which is the value I set for the last element in the array.
Okay, now the example is about struct. So let's make a struct.
And now what do we want to store in the struct? Well, the temperature. And
I would like to have now inside of such a temperature data thing, the array that we had before.
So I think, let's call this data. Yeah, okay.
Yeah, let's call it the data of the day.
How do we initialize this now? Well, let's create temperature data, call this Monday. We don't need to make an array now because the array is in the struct. And now we can do the same thing as we know from C and initialize this. I think I did with the same values.
Yeah, same values again.
Just so we have visualization so that it matches. Okay. And as we initialize an array here, we can do it the same when the array is in a struct. We can write it like this.
So this inner part within the inner curly brackets is basically the initialization list of the array.
And now we want to do the same thing as above, just with the struct.
Okay, so we log evening struct.
We said arrays are always passed as reference.
So you just pass the struct here, okay.
Oh no, let's not call it.
A day, maybe.
Day.
You pass a day here, yeah. And the measurement again. Okay, now how can we access the struct?
Yeah, so we said we do this with the dot, right?
Okay, yeah, it's
data,
basically just a dot.
like this.
Maybe we need to specify which position in the array.
Oh, right.
Yeah.
This is an array, so we need to say that this is at 2. You can rewrite this, rewrite it like this, and just replace temperature with day.data, and it works out too.
So, okay, we have this now. Then maybe copy your printf as well.
So now here we have Monday.data, and we get the second entry, no, the third entry.
Okay, so let's ask maybe.
Yeah.
What is the output of the second printf? It should be like we enter 4. So who thinks the output is now 4? And who thinks the output is not 4 of the second printf? Okay, so 2 people think it's 4, 2 people think it's not 4, and 60 people think there won't be an output. Okay, let's see. And
it's 0.
Output is 0.
So we said arrays are always passed by reference to functions, but structs are always passed as value to functions, passed by value. So they are copied into functions. Even if the struct contains some array, the array is copied into the function. So now this behaves differently than when I directly pass an array to a function. Do we have a visualization for that?
Yes, of course we have one. So this was just, we can skip this, we know this already. So this is now the important visualization here. So this was the array from before, and now this Monday variable is the struct. I indicated the struct with this box here, and inside of the box we just have a single member variable, which is this array of size 3. So this is data 0. If it's not readable, this is data 0, data 1, data 2, and here are the respective values. And now if we pass this struct to the function, then this struct, this gray box, will again be copied. So we have another struct, a copy of the first struct named day in this function, and this is now like passing an integer. They don't have to do anything together.
Yeah. Maybe to help you think about this, every time we use an array, it behaves like a pointer. So when we pass it to a function, it behaves like a pointer, and it's called by reference. But when we store the array into a struct, we are not really having in the struct, we don't have a pointer stored in the struct. As the same thing as we don't actually have a pointer stored on the stack, it's just a fake pointer. We don't actually store a pointer in the struct. The actual array is stored in the struct. And of course, when we use a struct like this, then it's just like any regular struct. And if we don't, and there's no pointer, so the whole struct is copied. So also the array is copied.
Maybe you can fix your program then. So can we now return the struct?
Yes. We could just return the new struct that we adjusted. Like this. And what happens here is we copy the struct into the function. In the function, we change the copy. We return the copy. The copy is again copied out of the function, and we overwrite our previous struct, the memory of the previous struct, with the new struct with the new values. And yeah, let's check this works now.
Yeah, luckily you also have a visualization for that. So we copy this value into the struct, and then if this function terminates, this gets removed, but we returned the struct from the function, so this box here will be again copied back, and that's why we have the value 4.0 then contained here.
Yes, but this is just like the same thing we did in A1. Instead of passing anything by reference, we always just pass by value. What can we do if we actually want to pass by reference? Well, we could take a pointer to a struct. This is of course something that works, and then we don't need to return anything. But here we already see an error.
Maybe fix the main function first, so we don't have the return value.
Yeah.
And we would like to get the pointer, so we pass the address.
The address of the struct now. But we already see an error here. And that's, of course, we changed this here to a pointer. So at some point we need to dereference it to actually get to the value we want to override. But now the question is, where do we dereference this?
What do we need to write there that it works?
Yes. So if we dereference this, we need the parentheses, because else the dot would bind higher in the operator precedence. So it would not work out. But if you put this in parentheses, then this works. You can try this. But the nicer thing, I think you saw this in the lecture, is we have this arrow operator here for the day, and this is exactly the same as if we do dereference and then the dot. because with the parentheses, this is really weird to write because you always need to put this in parentheses. With this arrow here, it just does both in once because this is really something you do very often. So there exists this arrow operator and we see it works. We dereference it, get to the array, change the array, and we actually change the array in the main.
And also here we have the visualization. So in this case, the struct remains just in the main function, and we instead have now the address as a parameter in the function where we want to set the evening temperature. And then, as usual with call by reference, if we want to set the value 8.2, we follow the arrow by dereferencing, then access the struct at the correct position, so at data 2, and then overwrite the value here. So, which then would be the 8.2. And then we did directly the change in this struct, and it's unimportant that this function terminates.
Oh, let's write here 8.2, so the visualization is the same.
Yeah, okay. Yeah. So the takeaway of that is really, if you pass an array to a function, you pass it by reference. If you pass a struct to a function, this is by value. And if it happens that the array is contained in the struct, then it is also passed by value.
So we need a pointer to the struct that contains the array. So this now seems that C has really many edge cases you need to consider. And yeah, I think that's the case. But if you get the hang of it, once you notice that the array is always the pointer and it behaves like the pointer, but it's not really a pointer, sometimes the size of works, sometimes it doesn't, and that if you have an array in a struct, it's always copied and not like a pointer like we had before. Once you really know this, then working with pointers makes much more sense than just now when you're trying to learn this. So if you practice this, at some point, everything will make sense.
Okay, so the string topic will be postponed to next week. So we are at the end now. So we have seen the first part. So we did the user input again with fkdes and getchar in this sweet little example. Then you showed us the two-dimensional arrays. And yeah, then we concluded with the structs and the difference with an array passed by value within a struct and by reference as it's just passed as an array.
Maybe just one more thing for the struct thing. Of course, you can have an array and other members in the struct.
Yeah.
Yeah, and then of course, everything is copied. So you could try this out at home, and then it also might make more sense.
Okay, then thanks a lot, and the lecture will start in 10 minutes, and see you next week.